Cities are heating up fast. But here's the thing. A tree is not just shade. It's actually a living, breathing air conditioner.
Welcome to This Explainer. Today, we're diving into exactly how trees cool our cities without using a single watt of electricity.
They basically pull this off in two totally different ways. The first is physical shade. Their leaves and branches physically block incoming solar radiation from hitting the pavement. But the second way is evapotranspiration. This is where trees move water from the soil up into the air, releasing water vapor. It's an active, living cooling system. To see exactly how powerful this is, researchers set up a study in a subtropical island park in China. They tracked everything: air temperature, humidity, solar radiation, and wind speed, both inside and outside these plant clusters, right in the middle of the summer heat.
And the findings? Absolutely fascinating. The biggest drivers for cooling weren't just about, planting more trees. What truly drove the temperature down were specific traits: crown area, canopy density, solar radiation blocking, and wind speed. That is the ultimate recipe for urban cooling.
So the really crucial takeaway here is that a good urban tree isn't just decoration to make a street look nice. It is literally climate infrastructure. Okay, let's dive a bit deeper into the exact mechanics of how this happens. Section 1, the science of cooling, sensible versus latent heat flux. First up, we have sensible heat flux. Think of this as how the tree's physical body, its leaves, its branches, its trunk, interacts directly with heat. It blocks and absorbs solar energy. Traits like leaf albedo, which just means how light or dark a leaf is, determine how much radiation the plant absorbs, rather than letting it bake the ground down below. And the sheer power of this is unbelievable. In that subtropical park study, specific plant clusters reduced solar radiation by a staggering 98.33%. They are essentially massive natural sun shields. But then we have latent heat flux. Now this is the active air conditioning part. Through a process called leaf transpiration, the plant pulls moisture from the soil and releases it as water vapor. That vapor increases the relative humidity and actively cools the surrounding air.
Section 2, plant traits that matter.
You see, the physical characteristics of a plant completely dictate its cooling efficiency. Things like leaf area index and crown diameter determine exactly how much shade gets cast. Albedo determines heat absorption. And stomatal density, well, that dictates how effectively the plant can actually transpire water into the air to generate that latent heat flux we just talked about. Here is a really fascinating comparison of how different plants react during a heat wave. Isohydric plants, like a lot of deciduous trees, will rapidly close their stomates under water stress just to save themselves. But anisohydric plants, like certain grasses, keep transpiring even when they're stressed. This means that, surprisingly enough, some grasses can actually cool a microclimate better than a big deciduous tree during extreme heat.
When researchers mapped out the data from that island park study, the mathematical relationships became super clear. Take crown area, for example. A larger crown area has a direct, measurable path to decreasing air temperature while simultaneously bumping up relative humidity. It's a proven system.
So, synthesizing all these mechanisms gives us the ultimate cooling process. Step 1, a dense canopy blocks the solar radiation. Step 2, stomates release water vapor into the air. And step 3, wind removes that thermal energy. Without wind, the convective heat transfer just stalls out. You really need all three working together for maximum cooling. Section 3, the diversity effect. It turns out just planting a single species of tree isn't nearly as effective as planting diverse plant clusters. Research shows that higher diversity herbaceous communities and forests create a measurably cooler environment, dropping microclimate temperatures by up to 2 degrees Celsius compared to just uniform single-species plantings. So why does diversity work so much better? Well, diverse canopies create greater structural complexity. This forms thicker boundary layers that essentially trap cooler, more humid air right there in the understory. It decouples that local microclimate from the much hotter macroclimate sitting above it, basically creating a protective thermal bubble.
Section 4, nature's climate infrastructure.
Going back to that subtropical park study, the maximum cooling effect they measured was a 5.19% drop in air temperature inside those plant clusters. That totally proves the incredible quantifiable power of these natural systems when they are structured correctly.
Looking at these multi-layered plant clusters, the takeaway for us is pretty clear.
Landscape designers and city planners absolutely must prioritize crown area and canopy density. We can't just keep planting isolated trees in tiny concrete squares. We have to engineer diverse plant clusters to maximize thermal comfort for the people living on the ground.
I want to leave you with this provocative thought. If trees are truly living air conditioners, what happens when we stop treating them like simple decorations and start designing every single city street as a connected, engineered microclimate? The science is there, the traits are measurable, and the cooling is very real. Thanks for joining me on this explainer. Next time you look at the trees outside your window, remember, you're looking at active technology for our future.